So the past two sections have focused on different types of quadrilaterals. For this particular section, 5-6, it is only going to focus on parallelograms. So in the past, ways of proving quadrilaterals was that you had to prove it by the definition. In this particular section, there's going to be 5 different ways to prove that a quadrilateral is a parallelogram. And what you're going to find is a lot of them are the properties. But it only works this way for a parallelogram. So it says any one of the following might be used to prove that quadrilateral ABCD is a parallelogram. So if both pairs of opposite sides are parallel, so that is the definition, then the quadrilateral is a parallelogram. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. If one pair of opposite sides of a quadrilateral is both parallel and congruent, so that's the same pair, both parallel and congruent, then it's a parallelogram. If the diagonals of the quadrilateral bisect each other, and if both pairs of opposite angles of a quadrilateral are congruent, then it's a parallelogram. And you have flexibility. Now, sometimes, depending on which one you pick, that'll lengthen the proof itself, but I'm going to tell you usually they are somewhere around 6 lines for whatever reason. The shortest route is usually around 6 lines. So let's try one of these. So we know that ACDF is a parallelogram. So the outside one is a parallelogram. And our goal, and we also know this angle equals this angle, and we want to prove that the inside one's a parallelogram. So step number 1, we're going to start with labeling some stuff about a parallelogram. Well, opposite angles are congruent, so I can say FAC is congruent to CDF. Just make sure when you're talking about a parallelogram, these are the only 4 letters you should be using because that's the only parallelogram that we know of. So B and E should not be used at all when we're talking about this. So opposite angles are congruent. If you want to put the other pair, that's fine as well. For number 3, I'm going to say opposite sides of a parallelogram are congruent. So A to F matches with D to C, and A to C matches with D to F. And then we write opposite sides of a parallelogram congruent. Remember, do not write property of parallelogram. You will not get credit for it. I need to know which property you're using. Then the 2 triangles on the outside are congruent by ASA. Then by CPCTC, I'm just going to label all the sides that are missing, or just not labeled, we'll put it that way. So we have that one. We have that one. Let's make sure we're in the right order. So F to B should go with C to E, and A to B should go with D to E. So that's by CPCTC. Then think, in order to be able to prove that we have a parallelogram, again, there's 5 reasons above. So far I have FB and CE congruent, so that's one pair of opposite sides. The question is, I need to either get the other pair of opposite sides, or I need to prove that that side is also parallel. So I already know AC, this one, is congruent to this one, and I just proved these 2 little green circles. Therefore, by subtraction, I can prove what's left in the segment is congruent to each other. And then at this point, that inside figure is a parallelogram because both pairs of opposite sides are congruent. Then we have a parallelogram. So both pairs of opposite sides, we can even say, of a quadrilateral are congruent. Then we have a parallelogram. Okay, so again, around 6 lines, give or take a few. All right, let's try another one here. So we have CAR is isosceles with the base of CR. AC is congruent to BK. And C and K are congruent. All right, so copy that down. Now, it tells us it's isosceles from the start. The key is it does not say which 2 sides are congruent. So you need to state that. So if they're saying that CR is the base, then you need a line that says that AC is congruent to AR by definition of isosceles. But as I'm labeling that, they need to have the same markings. Just be careful because we already have AC and BK being congruent. So what you might want to do is right off the bat, before you forget to add a line, say that AR is congruent to BK, which is congruent to AC by the transitive property. Remember, the transitive property, it links all congruent statements together. We have 2 congruent statements which make a congruent statement. Then after that, according to what we have, we know it's isosceles. So we can say that the angles opposite are congruent to each other. So angle ACR is congruent to angle ARC by the isosceles triangle theorem. And then just be careful. As soon as you write that, you don't want to forget. We've already said that angle C and K were congruent. So if we're now adding R into the mix, you want to make that connection there. So I'm going to say angle ARC is now congruent to BKC, which is now congruent to ACR, again, by the transitive property. You're linking two congruent statements to make a congruent statement. Now, if I'm trying to prove that this four-sided figure right here is a parallelogram, again, your options, we're not going to do anything diagonal-wise because that wouldn't make sense. We don't have diagonals. We're not going to do necessarily anything with parallel because we don't have anything parallel-wise here. For right now, in terms of both sets, we're not going to talk about both pairs of opposite sides because there's really no way of saying that AB and RK are congruent. But we do have one pair of opposite sides. So then the question is, the other option you have is, can you prove that that's parallel? It is congruent, but can you prove it's parallel? So let's look what we have. We have these two angles right here. Well, those two angles, if you think about it, if we were to extend these two lines, and this line right here is your transversal, those are corresponding, which means that AR is parallel to BK, because corresponding angles congruent implies parallel lines. And then now we know that AR and KB are not only congruent, but they're parallel, which means BARK is a parallelogram, because one pair of opposite sides of a quadrilateral is congruent and parallel, so then we have a parallelogram. All right. Number 3 says, given quadrilateral quad with angles shown, show that it's a parallelogram. All right, so let's see. So we got 4 sides, so let's set equal. Let's see what happens here. So I'm going to take my opposite angles. I'm going to distribute that one. And when I distribute that one, I get 3x to the third minus 15x squared. Well, that shows me that these two match up. So angle Q is congruent to angle A. If I do the same thing here and use my properties of exponents, I get x to the 10th on both sides. So since quadrilateral, you can just say, since both pairs of opposite angles are congruent, the quadrilateral is a parallelogram. And whether you use the symbol or if you want to write out parallelogram like that to abbreviate a little bit, certainly be my guest, whatever you're comfortable with. All right, let's keep going with practice problems here. All right, so given NRTW, so the bigger figure's a parallelogram, NX and TS are congruent to each other. I have to move the figure. Let's see. I'm just going to redraw it over here so I can write on it. B, T, S, R, P. Okay, so NX, TV, WV, PR. And we want to prove that that inside shape is a parallelogram. So step 1, the outside one is a parallelogram. We're going to use our knowledge. So using 3 letters, I'm going to say WNR is congruent to RTW. Opposite angles of a parallelogram are congruent. So I have that guy and I have that guy. And just if we look down at 7, you can certainly put these in the same line. I'm just going to actually show you that they're both there. I'm going to do the same for the other pair. So NWT and TRN, same thing. Opposite angles are congruent. So I'm just covering all my bases here. But 2 and 7 can be the same line. I'm going to write can be same line. I don't know why I split it here. All right, for 3, we know that NR and WT it should be NR and TW are congruent, and I think I have another one, yes. So 3 and 8, same thing. WN. So if it's WN, then it needs to be RT, and the same thing, can be the same line, because then that cuts 2 lines out of this proof. And then it's not 12 lines, it's 10 lines. So we had opposite angles congruent, opposite sides congruent. Those are definitely the most popular, and if you're trying to figure out stuff to use, just throw it out there and use it. It gives you more to work with. All right, so now we already have segments that are congruent, so we can use the subtraction property to say that NP, right here, is then congruent to VT, which is right here, by subtraction. Then if we look at our triangles, we have NXP and we have TSV are now congruent by SAS, because you have 2 sides and you have an angle. I think I labeled that one wrong, so give me 1 sec. Yes, I did. All right, let me just fix this. This goes here. All right, so now those 2 triangles on the bottom left and the top right are congruent by side angle side. Therefore, XP is congruent to SV. X to P goes S to V. So again, a bunch of these orders are flip-flop. These are from years ago. By CPCTC, then we've already done 7 and 8 because we said we were going to just regroup those. You can also, since you're using the same property, you can also chunk